So we have touched upon the idea of series and parallel circuits, but let's look at them in a little bit more detail now. So we have seen series circuits before. A series circuit is essentially when you have one loop or one possible way for the current to flow through the circuit. And so what that might look like is a very typical circuit that we've seen before. So put a bulb here and a bulb here, and we'll do an upper circuit like that. And you can see here there's basically one loop. Okay, that's it. The current can flow in this direction, and that's pretty much it. Now, for a parallel circuit, that's not quite the case, and we can take a look at that. So for a parallel circuit, there's going to be multiple ways for the current to flow through, and actually the circuit might have more than one branch. And so what that might look like is a very similar setup to our series circuit. So again, we'll have a lamp over here, but instead of putting the next lamp next to it like this, we'll draw another branch like that. And you can see here there's now a couple ways for the current to flow through the circuit. It can flow through the first loop here. It can also flow through the second loop like that. Okay, so there's two different ways now for the current to flow through, and this is what we call a parallel circuit. Now, series circuit and parallel circuits are slightly different, and they differ in the way that the voltage and the current is spread across components inside of the circuits. So let's take a look at a series circuit first. So for a series circuit, the total resistance of the circuit is just going to be equal to the sum of the individual resistances. So that would mean R1 plus R2, etc. And so what this means is that this lamp here would have a resistance R1, this lamp here would have a resistance R2, and if you wanted to find the total resistance, then we just add those resistances together. So if this was 10 ohms and this was 10 ohms, the total resistance would just be 10 plus 10, it'd be 20 ohms, and we can work out the total resistance for series circuits very easily. The next thing we need to know about series circuits is the potential difference. Essentially, the V supply is going to be over here. So whatever potential difference is from your battery or your cell, this is going to be equal to the potential difference that's dropped across each component. And what that means is, again, each component will have a specific resistance and also a specific voltage or potential difference across it. So if you were to take a voltmeter and measure it over here, then the total resistance or the total voltage would be equal to the sum of the individual voltages. Okay, so V1 and V2, and V supply is going to be spread across these voltages, or spread across these components. And in this case, because the resistances are the same, then V1 and V2 will actually also be the same amount of potential difference will be dropped across both of the components. But actually we can take a look specifically how the voltage or the potential difference is spread across the components when you have a series circuit. So let's take our circuit over here, and this time let's work with a couple of resistors, and let's say we have a supply voltage of 10 volts, and we're going to give ourselves a resistance here of 5 ohms and resistance here of 10 ohms. Then essentially what would happen is the resistance or the voltage will be split across these components depending on their resistance and proportionally to their resistance. And to work this out, we can work out the current in the circuit. So we know that the total resistance in the circuit is going to be equal to 5 ohms plus 10 ohms, is going to be equal to 15 ohms. And therefore we can use our Ohm's law now to work out the total current in the circuit. Remember, because this is a single loop, current will be the same in each loop. So if we were to put an ammeter here or an ammeter here, it would have the same reading. So we can use the total resistance and the supply voltage to work out the current in the loop. And so what we do is then we take our supply voltage of 10 volts and we divide through by the total resistance of 15 ohms, and that will give us our current. And if you do 10 over 15, you should get an answer of 0.6 recurring amps. Okay, so that is the current in your circuit. And then you can see that if you were to do Ohm's law in each of these individual components, so now we're looking individually, not at the whole circuit, then you can work out what the voltage or the potential difference would be across each component. So let's take the first component, and again it's just an application of Ohm's law. So this time our voltage is what we're trying to find out, and that's going to be equal to the current through the component, which you know is 0.6 amps. So we're taking the 5 ohm resistor first, and we multiply it by the resistance of 5 ohms, and if you do 0.6 recurring multiplied by 5, you should get approximately 3.3 volts. Okay, so the current or the potential difference across the first component, the first resistor of 5 ohms, is 3.3 volts. And you can do exactly the same thing with the second one. So let's use a different color here. So V now would be equal to our 0.6, and this time we multiply it by the 10 ohms, and if you put that into your calculator, then you should get approximately 6.6 volts. And what you'll notice here is that the voltage or the potential difference across the 10 ohm resistor is double the potential difference across the 5 ohm resistor, and the resistances are also doubled. And so what we can say is the potential difference is spread across the components proportional to their resistance. So in this case, because there was twice as much resistance in this component, it drew twice as much potential difference than this component. Okay, so hopefully that makes sense. So you could use either method, you could use a calculation to work it out, and also you can just see here the way that it would work is that you'd have double the amount of potential difference across this component than this component. But the important thing is that when you add these two together, they will still equal the supply voltage, because that is the rule for a series circuit. Okay, so now let's look at a parallel circuit. So that's series circuits we've looked at now. Parallel circuits do have slightly different rules. The first thing we need to know is about the total resistance. The total resistance, you can't just add up the R1 plus R2. It doesn't work like that anymore, and we don't need to know specifically how to calculate the total resistance, but we do need to know conceptually what happens when you add different branches to your parallel circuit. And the idea is that because you're giving additional methods for the current to flow, now the total resistance is actually less than if you were to add the resistances together. So what we can say is that the total resistance is less than R1 plus R2. So for the same equivalent resistances in a parallel circuit, you'd have a lower total resistance than if you were to arrange the resistances in a series circuit. Okay, so you can see here, that's why the total resistance is lower than if you were to add them together. And actually what happens with a parallel circuit, we need to look at the current as well. So previously we said that the current in any one loop is going to be the same, but here we've got two different loops. So what we can say here is you might have a current with our ammeter here, we could measure it, but then the current through here and the current through here would actually be different. And what we could say here is the current through here is I1 and the current through here is I2, and over here essentially you have what we call the total current, and this is the current before it splits. So what happens is the current, as you mentioned, it has two different ways to go. So it goes through here, some of it goes through here, and some of it goes through there. So what we can say is that the total current is equal to the current in the individual branches, okay, which is what we've drawn there. And so what happens is that when the current reaches over here, it joins back up again. So if you were to place an ammeter over here, you'd get the reading of the total current the same as you got over here. Okay, so that is how the current works, and you're probably thinking this looks a bit complicated, but luckily the potential difference, when it comes to the potential difference, is a lot simpler than even the series circuit. So the series circuit, before we saw how the potential difference was split across the components. Now luckily for us, when you come to a parallel circuit, it's much simpler than that, and actually the potential difference across each component through each branch is going to be the same. Okay, so through each branch, if you were to put a voltmeter over here and a voltmeter over here, you'd get the same voltage, and it would just be equal to the supply voltage. So if this is V supply, then this would be V1 and this would be V2, and essentially what we're saying is that V supply is equal to V1 plus V2. And actually we can look at this in a bit more detail, so let's just draw it out again. This is V supply, so V1 and V2 here is referring to the potential difference spread across the whole branch. So within a branch you might have several components, and the idea is these components that you've drawn inside of the branch are arranged in series. So if you were to look at this individually, this is the series circuit, and the potential difference will be split across components as we mentioned before. So here you have V supply, or just Vs. And what we're saying is that for a parallel circuit, if you were to connect up a voltmeter over here, this would give you V2. And if you were to connect up a voltmeter over here across all of these components, this will give you V1. And essentially what we're saying is that Vs is equal to V1 is equal to V2, which is what we said before, but the key thing to note is that V1 spreads across both of these components. Because these are both in the branch, the potential difference across both of these are going to be V1, but individually you're going to have a different voltage, a different potential difference spread across these components. Okay, and to work out what that would be, you need to know the resistances of these components, and you need to work it out like a series circuit. Okay, so hopefully that all makes sense so far, and let's actually have a go at now applying what we've learnt in a question. So this is a question we're going to be looking at. Feel free to pause the video and have a go. Essentially, we have a battery over here supplying 1 kilovolts, and what we're interested in is finding the voltage across this component here, this lamp over here. Okay, so have a go and then come back and we'll go through it together. Okay, so welcome back. Hopefully you had a go at that. And the first thing we can identify is we have a parallel circuit here. So you have the current going in two different directions. And with a parallel circuit, the voltage across each of the branches is going to be the same as the voltage that's supplied to those branches. And in this case, that is 1 kilovolt or 1000 volts. Okay, so we have 1000 volts across both of these branches. So now let's actually look at the branch we're interested in a bit more detail. So if we draw this out again over here, we've got an ammeter, we've got a resistor, and we've got a lamp over here. And what we can say is that if we were to take a voltmeter and put it across this whole branch, then that would be equal to the supply voltage, or the voltage that was supplied to it, of 1000 volts. So now what we can do is look at our ammeter, and our ammeter has a reading of 2 amps. Now this is quite important because now we're looking at a series circuit. All the components are arranged one after the other. And so what we can say in a series circuit, in any one single loop, the current is the same throughout the circuit. So if the current is 2 amps here, that means the current is 2 amps through this component, the current is 2 amps through this component, the current is 2 amps even after both these components. The current doesn't change, it's the same throughout this branch. And therefore, if we know that the current is 2 amps, and we know that this component has a resistance of 300 ohms, then we can use Ohm's law to work out what the potential difference dropped across this component would be. And so let's do that down here. We know that Ohm's law of V equals IR, and so we can just plug in our current of 2 amps, multiply that by our resistance, which is 300 ohms, and we should get a total of 600 volts, because we worked out the voltage or the potential difference. So now what we're left with is we have the total potential difference across these components, and we have the potential difference that has been dropped across this resistor. And if we remember from our what we know about series circuits, the total voltage is equal to the potential difference of the individual components. So in this case, the total voltage or potential difference was 1000 volts. So that has to be equal to the voltage across the resistor here, which is 600 volts, plus the potential difference across the second component, the lamp, which is what we're trying to find out. So we'll call that V2. And guys, I'm using voltage and potential difference interchangeably. In your exam, they will always use potential difference, but you'll get credit for using voltage as well, so that's fine. And so we can say that V2 is just equal to 1000 minus 600, and so hopefully everyone got that V2 has a voltage of 400 volts across it. Okay, so the lamp has a voltage of 400 volts. So hopefully that was useful, and I'll see you in the next one.